All right, so we're now going to talk about our first reaction, our first reaction with conjugated alkenes, and that is our HX addition to conjugated alkenes. So this was one of the first reactions we learned, right? If you take an alkene and treat it with HBr, remember we're going to follow Markovnikov's rule. We're going to protonate the alkene, form a carbocation, the bromine will attack, and the bromine will add to the more stable carbocation and will follow Markovnikov's rule. So we're really building on this reaction here, but now we're going to talk about a conjugated system. So we'll talk about our sort of simplest conjugated system. We'll use 1,3-butadiene, and we're going to now treat this with HBr, okay? And it turns out when you do this reaction, you can form two products. There's two products that you can form, okay? So let's just draw both of the products that we can form here. These are the two products that we can form. And what we're going to see is the major product will depend upon temperature. So the major product will depend on what temperature we run the reaction at. Okay, so we can control this reaction and the major product based on temperature. All right, so let's go through the mechanism so we can kind of understand this. This is the same mechanism we've seen before, right? Same mechanism as the reaction above. So if we have HBr, that's a strong acid. We have H plus and Br minus. Our first step we're going to do is we're going to protonate one of the alkenes. All right, we should note that these alkenes are symmetric. So it really doesn't matter if I protonate the alkene between 1 and 2 or 3 and 4. I'll protonate the alkene between 1 and 2. Okay, so when we do that, we'll still have our alkene between 3 and 4, and we'll now have a carbocation at carbon 2, right? So if I kind of draw in my hydrogens here, carbon 1 has 2 hydrogens, carbon 2 has 1, right? So I'm just going to draw the same molecule here, right? Carbon 2 only has 1 H. That carbon only has 3 bonds. Carbon 1 had 2 hydrogens, right? But because we added this H and we added that to carbon 1, right, we've now added our hydrogen to carbon 1 in blue on the left, right? That gives us a secondary carbocation. But this carbon is not just secondary, right? It's secondary allylic, which means we can draw a very good resonance structure with this, where I can move these electrons from between carbon 3 and 4 to between carbons 1 and 2. Right, so actually let's draw that. Let's draw our resonance structure up here. So the resonance structure we can draw for this is I can move this double bond between 3 and 4 here, right? In purple, that's our conjugated system. So we can form a double bond here, which means we now have a positive charge on carbon 4. Okay, so just important to keep track of our carbons. 1, 2, 3, 4, 1, 2, 3, 4, and now I have a carbocation at 4. So there's two paths we can go, right? Our bromine, if our bromine attacks carbon 2, right? If the bromine attacks carbon 2, then we get the first product we formed. We can call this the 1,2 product because I've added a hydrogen to carbon 1 and the bromine to carbon 2. Or in green, if our bromine attacks carbon 4 in the other resonance structure, right? So if that attacks carbon 4 here, right, 1, 2, 3, 4, we can call this the 1,4 product because we've added our hydrogen to carbon 1 and our bromine to carbon 4. Okay? So it turns out that there's two products that we can form. There's really two pathways that we can take, right? We protonate first. We form these two resonance structures. Now we have a choice. The path in red, the bromine attacks carbon 2 to form our first product, we're calling 1, 2. Or the bromine could attack carbon 4, right, to get the product on the right, our 1, 4 product. All right? This is the mechanism. We protonate, draw our resonance structures, and then attack. All right? Now, what's interesting about this reaction is, in fact, temperature can play a role on what the major product is, right? So how does that work? All right. First thing we want to do is let's look at the two products we can form, and let's see what the effect on what temperature is. So we'll draw that in orange. So the product on the right, this will be favored at high temperature. That'll be favored at high temperature. And for our purposes, we'll say anything kind of greater than room temp, right? Anything greater than room temp. And that's really going to depend on your substrate, but in our class, we'll just say anything higher than room temp will favor formation of that product. And the other product here is going to be favored at low temp. That'll be favored at low temperature, and that'll be anything that's sort of less than room temperature. Okay? So now we have to kind of determine why that's the case. Okay? Why that's the case. All right? So we protonate in orange, and then we have the red path and the green path. All right? So what we're going to do is we're going to draw an energy diagram of this reaction and the two paths, right, to kind of help see what's going on. Here's my energy diagram. Okay, I'm going to start with my initial product. There's my alkene. 2 steps, so we can protonate. Okay, we can protonate. This now is the 2 resonance structures that we can draw. Okay, so this is 1 intermediate, right, represented by 2 resonance structures, and then there's 2 paths that we can go. There's 2 paths. We can follow the green path, our green path, which is, sorry, let's redraw that. Our green path, which gets us our 1, 4 product, or we can follow our red path, which gets us our 1, 2 product. Okay, so what we should notice here is that why is the green product formed at high temp, right? This product is more stable. This product is more stable. And the product that's more stable, is called the thermodynamic product. This is called the thermodynamic product. The thermodynamic product is the product that's more stable. That's the definition of that. Why is the green product, what we call the 1, 4, why is this product more stable? Why is that more stable? The key here is to look at the alkene. If you look at the alkene in the green product, that is di-substituted. That's a di-substituted alkene, whereas the product in red is mono-substituted. So if you remember, earlier we learned about alkene stability. Remember, with alkene stability, the more substituted the more stable. So because the green product, the 1,4 product, is di-substituted, it is lower in energy, it is more stable than the 1,2 product in red, all right? So at high temperature, we're always going to favor formation of the more stable product, the thermodynamic product, and in this case, it's the 1,4, okay? What about the other product, the 1,2 product, the product in red? Okay, how can we form this product? This product here in red is called the kinetic product. It's called the kinetic product. And it's the kinetic product because the transition state is more stable. So if I zoom in here, right, this has a lower activation energy, or lower EA. It's got a lower activation energy. Okay, so the product in green is formed at high temperature because the product is more stable, but there's something about the red pathway here that's more stable than the green pathway. So we're looking at the transition from here to here versus the transition from there to there, okay? So there's something about this transition as we go from to form the 1,2 product that's more stable about that transition, all right? So what is that? Well, here we can compare when and how the bromine attacks our carbocation. So what you'll notice here is when the bromine is attacking this carbocation on the right, this is a primary allylic. But our intermediate, the resonance structure on the left, what type of carbocation is that? That is a secondary allylic. So when the bromine attacks here, it's now showing that this is secondary, which is more stable than primary, which means our transition state in the red pathway is lower than the transition state in our green pathway, okay? So the kinetic product, right, while the thermodynamic product, we're looking at the energy of the final product. This is the energy of the final product. We're just looking at really alkene stability. But the kinetic product is we're looking at where the bromine attacks. So when the bromine attacks the more stable carbocation, we get the kinetic product, and that's always going to be favored at low temperature, okay? Because it has a lower energy of activation. And what's interesting about this is, remember, if we go through the mechanism, we protonate, right? We protonate to form our one intermediate that has two resonance structures. So we protonate to form our one intermediate. But the act of attacking separates the two different pathways. If I attack here, I'm attacking a secondary, that's our red pathway. If I'm attacking here, we're attacking the green pathway. So it's the act of attacking that separates these two resonance structures. It separates the two resonance structures, all right? So what we really need to know here is at high temp, we're going to favor the thermodynamic product. That is the product that's more stable, right? Which will be the alkene that is more substituted. At low temp, we're going to favor formation of the kinetic product. That is going to be when our halogen, our halide, attacks the, and I'm going to use quote here, the more stable alkene. Okay? Because it's the act of attacking that separates the two carbocations. So when X attacks the more stable, sorry, not alkene, the more stable carbocation, excuse me. So the kinetic product happens when you attack the more stable carbocation. The thermodynamic product is favored when you form the more stable alkene. Okay, so let's look at this reaction again. Let's add temperature. So if I take 1,3-butadiene and I react this with HCl at 5 degrees Celsius, right? Room temperature is about 22 degrees Celsius, right? The product we're going to form, let's do our mechanism here, right? We will form H plus and Cl minus. We protonate. We form our secondary carbocation that has a resonance structure here. So this is one intermediate, two resonance structures. But at low temp, we're preferentially going to have our chlorine attack the more stable carbocation, right? And that is not separate until the act of attacking. So our product will be this. We're attacking the secondary allylic instead of the primary allylic. If we do the same reaction here at high temp, so let's say we treat this with HCl at 65 degrees Celsius. The mechanism is basically the same, right? We have H plus, we have Cl minus. We protonate. We form our carbocation. We draw the resonance structure associated with this. Here, the chlorine will attack the other structure, right? Don't forget you have to add the chlorine to carbon 4, and that will be the major product formed because this is now a di-substituted alkene as opposed to a monosubstituted alkene. Okay, so if I do this reaction and I don't give you a temperature, right, which I won't do, I will give you a temperature, you don't know what the major product is. But if I give you a temperature, right, low temp, you're going to attack the more stable carbocation, that will be the major product. High temp, you'll form the more substituted alkene, and that will be the major product there. All right, so this is our first reaction with a conjugated system.